Hi everyone, today we're going to be covering section 6.5 and this is about the trapezoidal rule. And so our goal really is the same as it was when we were doing rectangular approximations. We're still trying to estimate the area between a curve and the x-axis, but now instead of using rectangles to do that, we're going to be using trapezoids. So here's how it's going to look, and then we'll talk about how the calculation is going to work. So let's say I have this curve here, and so we're looking on the interval, from 0 to 3. So let's say I want to have 3 subintervals, and we're going to use trapezoids to calculate this estimation. So here's how it would look on the graph. When we're doing trapezoids, now we're going to use both the right and the left endpoints of each subinterval to make a trapezoid. So obviously here my delta x is going to be 3 minus 0 over 3, which is going to give us 1. So we have subintervals of length 1. So now I said we're going to use both the left and the right endpoints. So let's look at our first subinterval from 0 to 1. What I'm going to do is go from 0 up to the function, and I'm going to go from 1 up to the function, and then I'm going to connect those points to make a trapezoid. Now obviously it's hard to see here because there's not much difference in those values, but you'll see it a little more clearly as we go along. From 1 to 2, again, I go up to the function on the left endpoint, take the right, go up to that function, and then I make a trapezoid. Same thing for all 3 subintervals. So you can see a little more clearly on that one how our trapezoid is made. So now let's talk really quickly about the geometry of trapezoids. So normally here I'm going to draw one the way we're used to seeing it. And we know we have the height, and we have parallel bases, base 1 and base 2. And so for the area of a trapezoid, what we're doing is h over 2 times b1 plus b2. So that's just the area for a trapezoid. Now in terms of our trapezoid here, what we have to realize is ours are kind of turned on their sides. So that this is actually the h right here, and then I have b1 and b2. So what you'll notice is this h in the trapezoid is what we've been calling our delta x before. So the height of each trapezoid is just going to be determined by our delta x, which is really just the length of each subinterval. So although our calculations are going to look a little bit different, this is not much different. Sorry, I keep turning the page. Not much different from doing rectangular approximations. So let's go ahead and do an example to see how this would work. So we're going to estimate the area under the curve f of x equals x squared on the interval from -2 to 3, and we're going to use the trapezoidal rule. Now again, we won't draw this out each time, but I am going to draw it once just so we can make sure we know how to visualize this. So we're going from -2 to 3. And then, let's see, I'll have to go up to 9. Let's make this a little taller. All right, and let's go ahead and sketch in our graph. So this is going to be 4, and then 3, I'm going to go all the way up to 9. -1 is 1, and -2 is 4. So I'm going to try to sketch in something that at least resembles a parabola here. All right, so there's my curve. And so now I'm going from the interval from -2 to 3 using the trapezoidal rule. So now it doesn't specify how many subintervals, so we're going to go ahead and we'll divide this into 5 so that we have even subintervals. So I'm going to draw in my trapezoid. Now again, we're going from the left endpoint, we're using the left endpoint and the right endpoint, and sketching in the trapezoid. Now here from -1 to 0, that's obviously going to look more like a triangle because really my base over here is going to have length 0. Same over here, I go up to my right and connect. Now from 1 to 2, connect to make our trapezoid. And then my last one here, making our trapezoid. So that's the idea here. Should label this. So there's our trapezoid. So now we're going to use the same idea we did before. We know we have our subintervals of length 1. So I'm going to draw those out here. And again, we said we have to use the left and the right endpoints when we're doing our trapezoidal rule. So now I'm going to draw kind of my little lines on both sides. Okay, I'm also going to make a note that my h, which is also, we said our delta x, is just equal to 1. And I'm going to fill in these values. So I know at -2, my function value that I get right from the function is 4. At -1, it's 1. And I'm going to repeat here because now I'm doing left and right endpoints. So 0, 0, 1, 1, 4, 4, and 9. So now, if we go back to our formula, we said it was going to be h over 2. So don't forget that over 2. So we said our h was 1. So I'm going to have 1/2. And now I'm going to add up all of my function values. And so here I'm going to make it a little easier. So I have 4. But then I notice I have 2 1 values. So I'm going to do plus 2 times 1 plus 2 times 0 plus 2 times 1 plus 2 times 4. And then I just have my last value of 9 at the end, plus 9. And so now we're going to calculate that all up. So I have 1/2, 4, 6, 8, 16. So it should be 25. And we get here a value of 12.5. Okay, so our estimated area under that curve using trapezoidal rule with 5 subintervals is going to give us 12.5. So now we have something here on the bottom. It says connecting the trapezoidal rule with RRAM and LRAM. And so the idea here is that this trapezoidal approximation, which I'm just going to call T, is actually the average of LRAM and LRAM and RRAM. LRAM plus RRAM over 2. And so let's go to our calculators and actually verify that for the example we just did. So we expect our trapezoidal approximation should be the average of LRAM and RRAM. So let's use this function x squared. I'm going to go to my RAM program. Let's see, our interval was -2 to 3, so my A is -2, my B is 3. We used 5 subintervals, so I'm going to put that in. Oops, I don't think I put my y equals. Sorry about that. Y equals x squared. Now we can run our program. 5 subintervals. And so I get my left approximation is 10, and my right is 15. So we can see if we average 10 and 15, we would get 12.5. So that's kind of a nice way to be able to check that you did the trapezoidal rule correctly, is averaging LRAM and RRAM, assuming that you're given a function. All right, so now that we know how to do that, let's go ahead and do some more examples. Okay, so for number 1 here, it says for the following problems, we're going to use our calculator to calculate the area under the curve over the given interval using LRAM, RRAM, and the trapezoidal rule. So since it tells us to use our calculator, right, we're going to use our RAM program. And again, when it asks for trapezoidal, we just have to remember that that's the average of LRAM and RRAM. So the first thing we're going to do, so we don't forget, we know we need to have that function in y equals. So I have -x squared minus 2x plus 11. And then we're just going to go ahead and do our program. So we're doing from the interval -4 to 0. And then it says 4 subintervals. So we'll put that in. So now it says our LRAM left approximation is 34. RRAM is going to give us 42. That's our right approximation. And then all we need to do, 34 plus 42, divide that by 2, and we're going to get, for trapezoidal, our approximation is going to give us 38. Okay, so now we're going to do the same thing. We're still going to calculate the area under the curve. We're going to use LRAM, RRAM, and the trapezoidal rule using 4 subintervals. Now it says do not use a calculator. Obviously we could not use that RAM program anyway because we don't have a function. So we're going to go ahead and work these by hand. So I'm going to do part A here. I'm going to do LRAM. And so my intervals, I have 0 to 1, 1 to 2, 2 to 3, and 3 to 9. So we have to be a little bit careful here. I have my 4 subintervals, but I have to make note that they're not all equal lengths. So this subinterval has a length of 6, so we need to be careful to work around that when we do our calculation. So now for left rectangular approximation, I'm going to take that left endpoint, and so I'm going to go get those values from the table. 2 is 7, and 3 is 9. So now I have 1 times 4, and really I can do that for these first 3 subintervals. So 4 plus 6 plus 7, and then here I have a length of 6. So I'm going to do 6 times 9. Whoops, not equals, plus. So now I have 17 plus 54. So I'm going to get 71. Okay, so now we can go ahead. I'm going to scooch this up. I'm going to do RRAM to the side here. So same intervals, or subintervals, I should say. I'm going to take the right endpoint values. And again, I'm going to sum them up. So 6 plus 7 plus 9, and then I have to do 6 times 8. So I have 22 plus 48, which is going to give me a value of 70. So now I've got my left and right approximations, and now I need to use trapezoidal. So just thinking through this, I know that my trapezoidal approximation should be the average of LRAM and RRAM. So if I do this correctly, I'm looking to get an answer of 70.5. So let's go ahead and see if that shakes out. So this is our trapezoidal. So 0 to 1, 1 to 2, 2 to 3, and then 3 to 9. And again, for trapezoidal, I have to use both endpoint values. So let's see. Okay, and so now I have to be careful. Remember, for a trapezoid we said was h over 2. And remember, the length of each subinterval was our h, which is the same as our delta x. So now when I calculate this, I'm going to have 1/2 times 4 plus 6 plus 1/2 times 6 plus 7 plus 1/2 times 7 plus 9. And now here, my h is 6. So I'm going to have 6 over 2 times 9 plus 8. So let me scoot this up again, and let's see. So we've got 10 divided by 2. We've got 5 plus 6.5 plus 16 by 2 is 8. And then 3 times 17 is going to give us 51. So if we add those up, we indeed get 70.5. So our work kind of proves out what we already knew by knowing those are the average. All right, so let's keep going. All right, so now I want to talk for a little bit. We've kind of, I think I talked with a few of you about this when we were doing rectangular approximations, but we want to talk about whether an approximation is an overestimate or an underestimate. All right, so in order to determine whether your estimation using the either left or right endpoints, or I should say, I guess, using LRAM or RRAM. Okay, is an overestimate or an underestimate, we need to look at whether the function is increasing or decreasing. And so here, you can memorize these rules, but I think it's just helpful to be able to sketch in sub-intervals and see what's happening. So let's look just from, we'll go from -2 to 2 and just draw in what's happening here. So I'm going to go ahead, I'm going to draw in both on the same graph, and hopefully this won't get too messy here. I'm going to use orange and purple, and I'm going to draw an LRAM and RRAM. So let's look for an increasing function, what's happening if we use LRAM. So from -2 to 2, I'm going to use my left endpoints. So it means from my left side, I'm going to go over, up and over. Okay. So you can see here when I'm using LRAM that each time I draw my rectangle, I'm leaving out some of the area under that curve. So that means if I'm increasing and I'm using LRAM, I'm going to have an underestimate. On the other hand, if my function's increasing and now I go ahead and do RRAM, I'm going to use the right endpoints. Now for the subinterval here, I'm going to draw my rectangle up to the top and go over. And same for each one. From -1 to 0, it's going to go up and over. From 0 to 1, I'm going to use that right endpoint and go over. And from 1 to 2, it's going to be that right endpoint and over. So you can see I'm over now by all these amounts. So for RRAM, if I'm increasing, I'm going to have an overestimate. And again, you can memorize these rules, but I think it's easier just to be able to sketch it out to see what's going on. Now, let's look really quickly if we're decreasing. And so let's take a look again at LRAM. If I'm decreasing, let's look on the interval from -1 to -2. So -2, I go up to the function and over to draw my rectangle. I'm going to do the same thing here, and here, and here. So now LRAM becomes an overestimate. I'm over the curve by all these amounts. And obviously that overestimate would become less severe if I used more rectangles, but we're just illustrating the point here. Now if I look at a right endpoint approximation over the same intervals, now from -2 to -1, if I use that right endpoint, I'm just going to go up to the curve and over. And you can see now that we're creating gaps between the curve there, which is going to give us an underestimate. And these are types of questions you'll see a lot of times in AP. They'll ask you whether these approximations are going to be over or underestimates. Okay, we can do the same thing for trapezoidal. But now when we're talking about trapezoidal, it's not increasing or decreasing that's going to make the difference, but it's going to be whether the function is concave up or concave down. So whether, in order to determine whether our estimation using the trapezoidal rule is an overestimate or an underestimate, we need to look at the concavity of the function. And again, to figure this out, we're just going to draw in some trapezoids. So if our function is concave up and we draw in some trapezoids, I'm just going to go from 0 to 3 here. I know I have to use both endpoints, and I'm going to connect them. So it's really hard to see what's going on there. From 1 to 2, I'm going to do the same thing and connect the endpoints. Still kind of tricky to see. But 2 to 3 kind of helps us see here that if I'm concave up, trapezoidal rule is going to give us an overestimate. Now, if we're concave down here, I'm going to go, let's see, use intervals of 4 just to make this a little easier to see. So if I go from 0 here to 4, we're going to have kind of this first one is going to be a triangle. And then I'm going to go to 8 and connect. You can see here that when we're concave down, The trapezoidal rule is going to now give us an underestimate of that area. So again, these rules will always true, but I know that they'll always be true, but I know that personally, I would probably just sketch out a curve and draw in the approximations to figure out whether it's over or under. All right, so let's see. I think actually we'll stop there because that gives us all the major concepts. Then tomorrow in class, we'll go through the examples on the next page, and then you can get started with your practice.